Welcome to the demonstration corner. Today we are going to do a brief demonstration on the HFM-25 or the heat flow meter 25. But as always, we're going to do a quick turn with the camera to show you the instruments we have set up in the demonstration corner that are available for demonstrations and training. Here we have our MP2 series, which is for our portable methods, and it covers transient plane source, transient hot wire, and transient line source. It's a pretty versatile instrument. MP stands for measurement platform, thus the ability to use different types of method transient sensors. This is our transient hot wire, which measures thermal conductivity, thermal diffusivity, and volumetric specific heat according to ASTM 7896. This is our TPS2, which is our basic transient plane source method, covering range of 0.01 up to 500 watts per meter Kelvin. The following ISO 22007-2, and we combine these two methods to make the MP1. And this is our measurement platform 1, or MP1, which combines transient hot wire and transient plane source with many other capabilities, temperature, and new testing modules. And there's a new method we've added to this, which is the transient line source. So it's actually an instrument with 3 methods. Our guarded heat flow meter, or our GHFM, following ASTM E1530 for measuring complex layers or heterogeneous samples. Conductivity range is 0.1 up to 100 watts per meter Kelvin and up to 300 degrees Celsius. And our big brother to the HFM-25, which is the HFM-100. This covers much larger samples of 300 millimeters by 300 millimeters by 100 millimeters thick, thus the name HFM-100. And then we have an HFM-50, which is a smaller version of this. It looks identical, just smaller, which has maximum dimensions of 200 by 200 by 50. So the numbers after the hyphen are the thickness range, the maximum thickness. So why did we design the HFM-25? We designed this to measure small format insulation. Very often transient methods get used for measuring complex insulation type materials, high porosity, large pores, a large degree of heterogeneity, where in some of those, or many of those situations, thermal resistance and thermal conductivity via ASTM C518 is the preferred method. And most of the time we weren't able to do small format insulation because of the minimum sample size required for the classic heat flow meters. So what we did is we designed a basic level heat flow meter, which has a 1-inch flux sensor, so it's 1 inch square. The ideal minimum sample size for this is 50 millimeters square. And of course it can do much larger than that. We'll talk a little bit about that. But what you get with your system is a near room temperature heat flow meter. So this uses Peltier tiles or thermoelectric, where the top side is heating and the bottom side is cooling. The plate temperatures are 10 degrees to 40 degrees. So ideally what you're doing is picking a mean temperature near your room temperature and creating your delta on each side of that based off of the type of sample you're measuring. So the lower resistance the sample is, such as a thin sheet of XPS or a very thick piece of material, you want a bigger delta on higher resistance material and a smaller delta on lower resistance materials. And that's to facilitate the instrument's plate's ability to reach steady state conditions. So the maximum thickness on the HFM-25, again, the numbers after the hyphen, is 1 inch or 25 millimeters. It is manual open, and we'll talk about sort of how to set up a sample. Ideally, your samples are 2 inch, but of course you can do much larger than that. It is still only testing an active area of the 1 inch flux sensor plus the guarding of the material itself. But you're able to open the plates and insert samples that are much larger. You're just testing a much more localized spot. If you want to learn more about this, we can share that in a live demonstration one-on-one. But you can move this from location to location and get an average of values for a heterogeneous sample. But the real strength is in the ability to test small materials. So this is included with the instrument is a piece of NIST 1450E, which is the new generation of NIST material. We are not cutting it through its thickness. That's not allowed by the certificate, but you're allowed to cut it in sections. We include a piece of XPS, which is 2 millimeters thick, because along with the small format sample for insulation, you can test down to smaller thickness than you can with the other heat flow meters. So we can test down to 2 millimeters of XPS up to a thickness of 25 millimeters, as you see with the included NIST. So the basic steps for making a measurement would be to calibrate the instrument to your room temperature environment with a delta T appropriate to your sample. In this case, we've already calibrated the instrument over a number of ranges, and actually if you calibrate the instrument with a number of delta T's, you always have them. And then you can verify with these two materials that come with the instrument, you can verify those calibrations routinely. But we're going to measure what is typically a difficult material to measure by any other method than thermal resistance or heat flow meter. This is an aerogel blanket. This is about 10 millimeters thick, or 9.5 millimeters thick. Classic material. It's highly anisotropic due to the internal structure and use of aerogel. And we're going to be using a much smaller piece than you would need for a large heat flow meter. This is approximately 2 inch square. We're going to set this up, and we'll open the software and show you the typical setup and the steps, and then we'll show you the start of the measurement, and then we'll show you the data on review. The typical measurement time for the HFM-25 is in the 20 minutes to half an hour category, because it is a much smaller material, so it typically is a little faster. So I'm going to switch to so we've already calibrated the instrument, so we're just going to show the setup that you would typically do. So I'm going to just go to the other side of the instrument. Now, one step in the software is to make sure that we'll see it as a step, but I'm going to do it before I switch to the software. We're going to zero the digital thickness gauge, and that's done by just making sure there's nothing in it and it's clear of debris, and then pushing to 0. This thickness is a required input for the software. So for making a measurement, you would lift the upper plate and insert the sample, and make sure that you're covering, and I'm sorry the camera angle won't allow you to see it, make sure you're covering the flux sensor like that. Of course, if you were measuring a larger material, such as the same material, just larger square, it's a lot easier to set up. You don't have to be quite as sensitive. We are using a standard weight. That standard weight is part of the calibration as well. So when we calibrate with 1450E, we are using the same material, the same weight. And that becomes part of the experiment. So I'm going to revert back to the initial piece of XPS. So it's set up, it's covering the flux sensor, sitting in the center. The extra material on each side provides passive guarding through the material. And we're going to switch to the screen, and I'll start the software. So here is our heat flow meter software application. It will auto-detect itself, so we'll wait a moment until it detects what's connected to it. HFM-25. Now we're going to proceed, and here it gives you the steps of what I've already performed. I just did it in reverse just to allow us to proceed with the software without switching the cameras back and forth. But you can see that it wants you to zero the thickness, which I've already done, so continue. So here's where we can run a measurement. So I'm going to click this. I'm going to load the calibrations we've already created using NIST 1450. And so we've created a number of delta T's by changing the upper plate and the lower plate temperatures, all at the mean temperature of 25, because our room temperature here is very near to 25. So all of these are just different 30 degrees all the way down to 5 degrees, so it allows us to test very small resistances. We're going to pick a 20 degree delta. That's our typical delta T for such a material, because this is, even though this is only about 9.31 millimeters, it's quite resistive. So we're going to use that, we're going to run an experiment at that temperature against that calibration. So here we're going to name the sample. And the clamp thickness is 9.31 millimeters. and I'm going to start calibration, or rather start the measurement. We're going to name it. This is where you want the data saved. We'll just put it on the desktop for now, and we can start the measurement. So here's our measurement proceeding from room temperature. So each plates were sitting at room temperature. There's no external cooling needed. That's all fan-cooled thermoelectrics. So the 2 plate temperatures will start to heat and cool to their corresponding temperatures that we set, which, as you can see above, which is 35 and 15 degrees. So we can wait a moment. Actually, what we'll do, we'll go look at the review data on the same sample, and we'll come back and you'll see the plates start to go to those temperatures. Before I leave though, the status, you have a continuous update of status. So right now it's running the measurement. Here, the thermal conductivity and resistance are listed, and they go from red to green. Green meaning you have acceptable steady state condition. And here on the right side is our composite flux between the 2 flux sensors. So ultimately we're looking for the plates to come to temperature and stay at those temperatures stably, and we're looking for the composite flux to be steady state condition. So the instrument itself looks for stability criteria, and then it proceeds saying once it's accepted, and it monitors that steady state condition for a length of time, and then once that's achieved, the results will be displayed and your measurement is complete. And over here it'll say complete. So let's open up the software again. We're not going to let it detect itself. We'll just use that for reviewing the software. So we're going to quit. Oh, I didn't mean to quit. I mean, we're not going to let it detect itself. So we're going to open an experiment. So here's the aerogel blanket, and here's a complete measurement. Upper plate. So this one was done with a slightly different range of temperature. It doesn't matter as long as we achieve steady state conditions. So this one, the upper plate was 30 and the lower plate was 20. So of course there's quite a bit of flexibility on what you can use for the delta T. Test is complete. That measures at 0.013 watts per meter Kelvin, which is in lines with the production, the manufacturer of this aerogel blanket, which uses ASTM C177 or guarded hot plate. That measurements within 5% of that the specification by that method. Yeah, that's a full demonstration. We can go back to the experimental software and sort of see the progression of the experiment, but this will take about 20-25 minutes to complete. So that's a complete demonstration. And if you guys have any questions, I will wait around for a moment, and then we'll tomorrow we have a demonstration on the HFM-100, and then the next day we have a demonstration on the guarded heat flow meter, the 2 that I showed you at the first part of the demonstration.